Hello everyone. Today we're going to design a cloud storage system, one like this. It's a kind of architecture that powers the apps we use every day. Google Drive, Dropbox, iCloud, you name it. But how does all of this actually work under the hood? I know it looks a bit complex right now, but don't worry, we are going to break it down piece by piece and understand it. Let's dive in. We interact with all kinds of files every day, photos, videos, and documents, and we often access them from our laptops and mobile phones. But storing everything on your devices has problems. You could lose your phone, your laptop could crash, or you simply run out of space. Instead of saving all your files on your phone or laptop, store them in cloud. This means your data stays safe and you can access it from anywhere, anytime using any device. Simple as that. Alright, now we have a basic understanding of what cloud storage system is. Let's talk about the foundations of any system design, the functional requirements. Basically, what are the things that system needs to do? What can user expect from a cloud storage system like Google Drive or Dropbox? Let's take a look. Functional requirements. Let's start with the most basic functionality, uploading files. When a user uploads a file, it should be transferred from device to the cloud storage safely and reliably. Next, downloading. User should be able to fetch any of their uploaded files on demand, no matter which device they are using. And finally, syncing. This is where things get tricky. When users edit or update a file on one device, the system has to make sure all your other devices catch up fast. Everything should stay in sync like a well-rehearsed dance troupe. Alright, to start with, let's just build a basic cloud storage system. Something that's simple, something that works. Let's forget about the scaling for the moment. Say it only handles 10 users, no massive code, no global traffic, no fancy infrastructure. Just clean, functional setup that gets the job done. This gives us a foundation that we need before things get complicated. Let's start with the basics. Our cloud file storage system needs just a few core components to get up and running. First, we have the user, someone who uploads or downloads files. This could be from a browser or mobile app or a desktop client. Next, the user sends the request to the server. Next, server. This server is the brain of the system. It handles incoming requests, authenticates users, manages sessions, and decides what needs to happen next, like saving a file or retrieving one. Then we have database. This is where we store metadata about the files. That include things like who uploaded what, where the file is stored, when it was last modified, and how big is it. We usually use a relational database here, something like PostgreSQL or MySQL, because it handles structured data really well. Finally, file storage. The actual file content, your photos, documents, videos, is saved in this file storage system. At a small scale, this could be just a folder on the server, but in real-world systems, we eventually upgrade this to a cloud storage like AWS S3 to scale better. So at a basic level, the user talks to the server updates the database, and the files are saved to the storage. It's simple, but this foundation is what will scale up later to support millions of users. Now that we have an understanding on components of this simple system, let's take a look at how uploads and downloads work in this simple system. Let's see how uploading of file works in our basic system. The user starts by sending a file to the server, say a photo or a document. The server first processes the file and gathers some information and important metadata, like the file name, its size, and the last modified timestamp, and who uploaded it. Next, the server sends the actual file to the storage system. Once the storage system confirms the upload and responds with the file's storage location, the server takes the location and stores it along with the rest of the metadata in the relational database. Only after the metadata is safely stored in the database, the server sends a final response back to the user. Your file has been successfully uploaded. And of course, the user is happy. Let's talk about downloading. First, the user sends the user ID and file ID to the server. Now, the server takes this user ID and file ID and asks the metadata database, saying, hey, give me the storage location of this file which belongs to this specific user. Once the storage location is received, server fetches the file from the storage using this storage location and responds the user request with the required file. And of course, again the user is happy. Alright, at this point we've built a simple functioning system. It works, but only to a point. This setup isn't built for real-world systems. A single storage disk can't handle petabytes of data. One server won't survive under millions of user requests. And scaling files across devices and users, that's just not happening here. So let's take this system to the next level, step by step, and see what scalable production grade architecture looks like. Let's scale our basic system to support multiple users. A single file storage cannot store all the user files, so let us use a scalable storage solution like S3, which is pretty resilient and can store huge amounts of data. Now, a single server will no longer be able to support millions of requests. Let's scale this to a cluster of multiple servers with a load balancer attached to it. Now, let's introduce block servers to support and optimize file uploads, and introduce a queue between block servers and server cluster. S3 is now connected to both the server, that is block servers, and server cluster. Also, let's introduce a cache for faster metadata access. And now introduce a cold storage. It's just an efficient way to store files that are not frequently used. Then, the notification service, which will notify the users about events like uploads and updates on the files. Last but not least, relational databases are now a cluster instead of single database. This ensures the reliability of the system by maintaining multiple copies of the data, just in case. Now that our system is all scaled up, let's put it to work. Time to see how uploads, downloads, and real-time syncing actually happen in this architecture. Let's talk about the uploading in the scalable system. First, the user or client application, basically the application running on the client's device, something like an app or website. I think you get the idea. Okay, this application simultaneously sends the file to block server for uploading the file and sends a polling request to the notification server. Polling request is basically asking the notification server to notify the user once the upload is done. On the other hand, block server takes the file, convert them into small blocks and store them in the storage. In this case, it's S3. And when acknowledgement is received from storage or S3, block server sends the block storage information to API server, so that this information can be stored in the relational database and cache. If you remember, this is similar to simple architecture. Instead of blocks, there we store the file location. Anyways, this stored block level information is later used to retrieve the files. Once the block storage locations are stored in the database and cache, notification service listens to the update and notifies the user about the successful upload. Okay, let's talk about the downloading functionality in scalable systems. First, the user sends a request to the server with the user ID and file ID. Now, the server first asks the cache, hey, do you have the information about the blocks related to this user file? If the cache says yes, then of course, it sends the block locations of the files. Here, B1, B2, B3 means block 1, block 2, block 3. Now, server goes to the storage, in this case, it's S3, and gets the required blocks and assembles them into a document and sends it back to the user. If you're still watching, first off, you're awesome. You're clearly serious about learning system design, and that's rare. We have actually covered how uploading and downloading works in scalable systems. Now, there's just one piece left, that is syncing. You have probably used Google Docs and seen how multiple people can edit the same file at the same time. But how does it work actually under the hood? Let's break it down. Let's talk about how two files are synced. Okay, let's talk about the setup first. Previously, a file is uploaded to the database, right? Now, red user and blue user are, let's say, collaborating on this file. All we are going to talk about is how does the file changed by the blue user is updated to the red user in real time. First, let's start with red user. Red user is working on a file and so sends a long polling request to the notification service. Now, red user is waiting if there is an update on the file, while, of course, editing the file. Let's talk about the blue user. Blue user updates the file and press the save button. As a result, a request is triggered to save the locally updated file to database. Now, block server receives this request along with the file and converts this file into blocks. Till now, very similar to how upload works. Next, block server figures that only, let's say, first page of the document is edited and rest of the file is exactly same. So, discards the unchanged blocks. Just the updated blocks, which is blue in color, let's say that's the first page of the document. Now, this block is saved to S3. As the acknowledgement is received from S3, an event is sent to the event queue to update the new block location in the database. Once that's done, a notification is sent to the user that the block is updated. Remember, red user was waiting for any update on the file. Finally, red user receives this notification. Now, the red user knows that there is an update on the file. So sends a request to fetch the updated block. As server checks for the recently updated blocks and gets the location of the recently updated blocks of that file, this block is fetched from S3 and sent back to the user. Finally, red user is in sync with the blue user. Alright, we have officially built our own cloud storage system from grounds up. But here's the thing, real world systems are rarely perfect. They need to be resilient and smart enough to handle failures, scale and edge cases. So before we wrap up, I've dropped a few thought-provoking questions in the video description below. Thinking through them will seriously deepen your understanding. Take a moment to explore them, and if you crack any of them, drop your thoughts in the comments below. I'm also planning to make more videos like this, so if there is a system that you want me to break down next, just say the word. Thanks for sticking around, you're awesome, and I'll see you in the next one.